page,
13.
and you want 14?
No, I'm just, oh, yeah, never mind.
All right, so the first one, the Goldilocks, started with Goldilocks. Mama Bear stores 3 bowls of porridge. Papa Bear got the large bowl, 2 liters. Mama Bear got the 1 liter. Baby Bear got the 0.5 liters. Later, the young burglar breaks in, tries different scents of porridge. She finds Papa Bear's too hot, Mama's too cold, Baby's just right, temperature-wise. Now, if all 3 were served within a minute of one another, and if Goldilocks cannot tell the subtle differences in temperature, what's a valid explanation for the temperature differences among her sample? All right, so on that one, I've got, you would expect if I had 3 samples, you would expect that the larger quantity would maintain its temperature longer because it's got a greater mass. I know that the energy required to give up a temperature, MC delta T, capital T, that mass, the greater the mass is, the more energy it needs to lose in order to change the temperature the same amount. So this maintained most of its heat, as one might expect. This lost more heat than it would be expected, and this lost somewhere in between the amount of energy. So what could cause this to lose more energy, or at a greater rate than this?
Could it be the type of wall it's in?
And I would have accepted that. The more surface area, the more that's closer to it. I mean, if you're trying to cool off pretty much anything, if you can spread it out, it will cool off more quickly.
So if the bowl was wider,
I was gonna say it'd have to be the first bowl being served.
The first,
Bowl to be served, because of time, it's the change
Ah.
of time.
did I put the wording on that to try to?
I know you said something about a minute.
yeah.
They were served within a minute of one another. So, and that's why I threw in the Goldilocks can't tell subtle differences in temperature, because if there's within a minute, I'm assuming that that would not explain the larger temperature differences that Goldilocks would notice. So bowl shape was actually the idea that I had when I wrote the problem. I think somebody made the argument of the porridge was not an even temperature to begin with. That, and, you know, anybody who's burned stuff on the bottom knows that it's hotter on the bottom than it is on top.
Or what if it was different types of porridge? Could it be that?
Ah,
Because it says 3, when the burglar comes in, it says the different types.
served 3 bowls of porridge. I did not say from the same container, from the same pot, so yeah, I would have accepted that.
And then,
Also with more modern take on it, you possibly could have popped one into the microwave or 2. They usually leave that part out of the Goldilocks story. There you go, $1 million idea for one of you.
but when I was talking about the bowls, I wasn't necessarily talking about, more surface, I was talking about maybe one bowl's metal and the other is wood.
Ah, okay, one's more of an insulator.
Yeah.
Yeah, that also, I think, a valid approach. I like the problem. Unfortunately, it depends more on life experience than on what was done in class, but. Oh well, not every problem's a winner. As long as I don't have to take the test. Sorry, that was Mom's attitude about cooking. She wasn't gonna eat what we were eating, so it didn't matter if it tasted good or not. No more eggshells I found in my food.
Ooh.
Yeah. And I do appreciate her making my lunch when I was a youngster, but surely she should have seen the mold on the bread. Anyway, I digress. I'm making her sound horrible. She is not. Cooking was not her thing. That's right, there's number 13. Two wave pulses are headed for each other. The pulses have the same speed and amplitude. The leading edge are initially 4 meters apart. The distance from the leading edge to the trailing edge is 1 meter. Okay, so we have the following setup. That's going this way. That's going that way. If the problem starts, they are 4 meters apart. This is traveling at 1 meter per second. This is traveling at 1 meter per second. Distance from here to here, I believe, was 1 meter. Let's just make sure that I read that correctly. Two wave pulses headed towards each other. There is a picture showing the one up and one down. Pulses have the same speed and amplitude. Leading edges are initially 4 meters apart. Leading edges, and the distance from the leading edge to the trailing edge of each pulse is 1 meter. Okay. How long before the leading edges meet? Well, how long?
2 seconds.
Yeah,
2 seconds.
because in 2 seconds, each will have moved to this point right here, so they will meet at that point at 2 seconds. So that's part A. Part B, how long before the waves pass each other? Well, at 2 seconds, it's gonna look like this. But that's going this way and that's going that way.
At 4 seconds, when they be right on top of each other.
Well, in force, so this is at 2 seconds, and then at 4 seconds.
Yeah.
So this is 2 seconds. At 4 seconds, this will have traveled 2 meters, and that will have traveled 2 meters.
Yeah, so it will look like a circle.
So no.
Yeah, okay.
So that's 2 meters there, that's 2 meters there. At 4 seconds, this will have
Past it.
traveled, let's see, that will travel 2 meters. 1, 2. And that will travel 2 meters, it'll look like that. At 4 seconds. That is awkwardly drawn.
What would it look like at 3 seconds?
So it's gonna travel 1 more meter, so it's actually set up. Ooh. So if we did something that might write, there we go. 1, 2, 3, 4. Oh, let's see if I can do this to scale. So if I make each of these a half meter, from there to there, so it's 1 meter across there, so then 1, 2, 3, 4, and then the other one here. So that's 1 meter. They're traveling 1 meter per second. This is gonna show up better than anything. All right. So after 2 seconds, this will have traveled, the front leading edge would have traveled to here. Still traveling this way, and that one's traveling that way. After another second, I believe that's what you said, so this is t is equal to 0, t equals 2 seconds, t equals 3 seconds. This will travel another meter, so this will be here. And this will be there. So that would be 3 seconds. And the question is, what happens halfway, oh, okay. So how long before they pass each other? So at 2 seconds, the leading edge touch. At 3 seconds, they're passing each other. And so the next question is, halfway between those, what happens? All right, so going with the hand gesture there. So halfway between it, the top wave is there, the bottom wave is there. So that's at 2.5 seconds. But what would that look like? I think I gave partial credit, that was your answer.
Would it look like one? Like flat?
Oh, okay, so not one of the bumps, but just straight flat line? Yeah, because I have a certain amount that's trying, there's this pulse in the rope pulling it up, a pulse in the rope pulling it down. They're gonna balance each other out, and you end up with, in essence, there's a node right there.
Oh, no, okay.
What happens when you have the two waves that add together and get you less than you started with? What is that called? Talked about it when we were in the hallway.
Deconstructed?
No, but you were sort of combining the two words.
It's one of the interferences.
Pardon?
One of the interferences.
It is indeed one of the interferences. It's not deconstructed.
No, constructed.
Constructive interference does not get you less.
Destructive interference?
Yes, constructive. Constructive is you add, you said deconstructive.
Oh.
You sort of combine the, put the D and the con in there. It is destructive interference when they overlap because they're on opposite sides. If they are on the same side, you get constructive interference, and when they overlap, you would end up with something twice the size of what you started with, in theory.
So what was the answer?
Depends on, so what happens halfway between the times in A and B? And then I have either in parentheses followed by nothing, so it looks like something got lost there. So visually, they would flatten out, they would cancel each other out. In words, destructive interference. And then the last one, let's see if we can actually get this to work. Any questions on this before we tackle the problem? Was there a need for 14? No? Okay, never mind. Any other questions on this?
Number 4. Sorry. And that's my last one.
Using the ideas of sound creation, propagation, and reception, explain how clapping works. What causes sound? More specifically?
Compressed.
Say it again?
Compressed.
Yeah. And I guess potentially you could get a small little sound if suddenly the pressure dropped, but you primarily get the sound when the pressure hits it. So in order to hear a clap, you need a compression wave. So how does a clap create a compression wave?
Bring your hand together and let your fist push down.
Yeah, pretty much that. So you bring the hands together, you're physically compressing the air in between them, but because it does get forced out from between your hands, that's what really gets that in essence is where the clap comes from, is at the very end. And if I just don't touch hands, you don't really hear it particularly well, even though I have forced air out. So you bring your hands together, and you create this pressure, this high pressure wave, then how does that get to your ear?
Is it like the metaphor, I guess, of the throwing the rock in the water, the waves will just.
Okay, you could connect it to that. Let's see if we can flesh that out some. Because the air that comes out from my hands is not the first bit of air touching your ears. That's, you're not hearing that air. How does that compression wave reach your ear? I assume you're just sort of thinking through it, Ashlyn, and not.
The ripple of like the speed of sound and like the ripple, like what Chase was saying, and it hits your eardrum and then
All right, let's talk about that ripple. How do we get that ripple?
the compression of air and how it's so weird. I know the question. I did it the other day. They had like started with a P or something, didn't it?
What's the last thing you said?
It started the word. Started with a P.
Propagation.
Yeah.
So how does it propagate?
Oh.
If the air from between my hands is not actually hitting you in the eardrum, how does that signal get sent to you?
Air. The ripple.
How does the wave propagate in the air?
Through molecules.
By moving molecules.
All right, so almost there. I have molecules of air between my hands.
Yeah.
I bring my hands together. It creates a pressure wave because it gets forced out from between my hands.
And
What
they-
happens to those molecules right there?
They move faster.
They bump into others.
Oh, they bump.
There's the key. They hit other molecules, which hit other molecules, which hit other molecules. Eventually, they'll hit a molecule that's going to pound you in the ear. That's the propagation. It's a longitudinal wave.
It is a long.
It is indeed longitudinal. And similar to when you snap your fingers, what you actually hear is the finger hitting the palm. It's not the fingers actually going against each other. You build up this energy in your fingers with potential energy. It releases into kinetic. The finger slaps your palm. That creates the compression wave.
But it's moving the molecules, hitting each other faster at a faster rate. That creates the sound. Or it's just they're hitting each other.
When I force the air out from between my hands, it does make the air molecules move faster, which will hit other ones. I mean, so yes, what's hitting your ear is going to be moving. Well, wait.
That's what I'm wondering.
It does force it out faster,
Uh-huh.
but because it forces out faster, you get sort of a bunch of molecules sort of stacked up with each other, and that's the pressure wave. Once it leaves your hand, then how fast it travels is however fast the air will take it. I have no control over that.
So did you say the molecules hit each other into it and makes your ear?
Yes. That molecule tells a friend, and that molecule tells a friend, and so on, and so on.
Are we gonna have to change, I guess, what's the word? From a solid liquid to a gas? For,
Phase change,
yes, thank you. Are we gonna have to do that for the exam?
it's fair game.
Okay. Can we, you're gonna give us the Q equals MC over, or MC change to T, you know, those formulas?
They'd be on the front, you have to be able to look at those
Yeah.
formulas and go, okay, that's the one that I use here.
Yeah, okay. And then can we go over one problem with like a metal cube in a large room, and it's
The rate of
chamber
cooling?
temperature. I'm sorry?
The rate of cooling?
Yeah.
All right, and again, the reason why it has to be a large room is that if it's in a small container, then the environment, like we did in the lab, where you took the hot cube, put it into a cup of water, the water's gonna change temperature, as I think all of you noticed. If it's in a large room, we assume that the temperature of the room is not changing significantly, because otherwise it becomes a calculus problem, because the amount of temperature it can lose changes because the environment's getting hotter. So, large room, we assume that the room does not change temperature. And so, in essence, it's this idea that objects cool at a rate proportional to temperature of object and temperature of environment. So if I have something at 110 degrees Celsius, we'll just say I've got an aluminum block, 100 degrees Celsius, and I stick it into a very large room, and after 10 minutes, it is now 90 degrees Celsius. The room it's a very muggy room. 30 degrees Celsius, so about 90 degrees. Quick and dirty rule of thumb that goes from degrees Celsius to degrees Fahrenheit. Very quick and dirty, double it at 30. There are more official methods, but that's if you need to do something quick. All right, so the first thing we need to figure out is how much did we actually lose and how much is it possible to lose? Well, that's how much we lost. We lost 20 degrees Celsius.